Good morning, boys and girls. Mr. Davis on location again outside the Perry Nuclear Power Plant. No, I'm not standing in Springfield getting ready to meet Homer Simpson, but I am getting ready to introduce to you today's topic of electricity and electric current. Just a little brief history on the Perry Power Plant. The Perry Power Plant is located about 40 miles to the northeast of Cleveland, and it's sitting on 1,100 acres of land adjacent to Lake Erie and is owned by Energy Harbor. Officially designed as a 2-unit installation, which is why you see those 2 cooling towers behind me, the operation of the second tower was canceled in 1994, thus which is why we only see 1 operating here today. So, operating on this single reactor alone, the Perry Nuclear Power Plant can generate up to 3,758 megawatts thermal power. To put that into perspective that you might understand, 1 megawatt thermal can generate power for up to 1,000 homes. Now, after running some numbers, this power plant on the single reactor can supply enough electrical energy for up to 3,750,000 homes. That is absolutely incredible. Let's see how we're going to be using electricity today in our discussion and our lab. Alright, boys and girls, welcome back to my office. Before we get into today's lesson, I want to review a little bit of what we did last week. Now, if you remember, we discussed the conversion from potential energy to kinetic energy, and we got inspiration from NASA in designing a landing craft that would hopefully prevent the breaking of our egg, which represented an exploration rover, and the landing craft, represented something that NASA would send to the moon or Mars or another planet for exploration purposes. Now, at the end of the lab, I extended a question to you and asked you if vehicles from the 1950s and vehicles to the 2000s had any differences in safety. And if you did not do that, I have a video illustrating just those differences. And what we're going to do now is we're going to take a look at that video, and hopefully you learn something that parallels what we did in last week's lab.
That's the Insurance Institute for Highway Safety's front crash of a 2009 Chevrolet Malibu and 1959 Chevrolet Bel Air. In slow motion, you can see the differences in how the new and classic cars perform in this version of the traditional frontal offset test. The Institute conducted this test to commemorate its 50th anniversary, and it dramatically shows how much improvement has been made in passenger protection since the nonprofit organization opened its doors. The 2 cars collide in an explosion of metal, glass, and plastics. Where the Malibu crumple zone absorbs much of the crash forces ahead of the windshield, the Bel Air structure allows the lighter car to compress the passenger compartment. The impact is made worse for the Bel Air driver by the lack of airbags, head restraint, and even a seat belt. As a result, injuries to the neck, chest, and both legs would be likely. Consequently, the Bel Air receives a poor rating across the board. On the other hand, the modern Malibu provides good protection, with the dummy movement being well controlled. Measures indicate a low risk to most body regions, though a foot injury would be possible. Beyond the safety gear, advancements in vehicle engineering give the Malibu a clear advantage in this matchup. While classic cars are often considered to be rock solid, this 59 demonstrates how much better today's cars are. And the IHS has played a key role in driving these advancements. In the past 50 years, the Institute has made a real impact. The roads today are safer for it.
So in today's lab, we're going to be discussing electricity, and in that process, we're going to talk about electrolysis and electroplating, which also is going to tie into our lab. However, before we do that, we have to know what electricity is, where it comes from, and how it moves. Today's objectives, we're going to be creating an aqueous solution, which is a liquid solution, of copper acetate using the process of electrolysis. Basically, all that means is we're going to take a big chunk of copper and we're going to dissolve it into a solution. Atoms are made up of neutrons, protons, and electrons. Protons are positively charged and electrons are negatively charged, where neutrons have a neutral charge. So what is electricity? Electricity is the collection or flow of electrons in the form of an electrical charge. Here we have the girl with her hair standing up because she has a negative charge about her. And then we have all these lights over here on the side of the screen. So electricity that moves. Current is the flow of electrons from one place to another, and it's measured in amps. There's that word again, kinetic energy. So electricity also has kinetic energy because it's energy in what? Motion. So how can we control the currents? Well, we can control the electrical currents through circuits. And a circuit is a path for the flow of electrons. So we have two types of circuits. We have a series circuit, okay, and then we have what we call as a parallel circuit. So our series circuit is where the components are all lined up in one path. And if that circuit is broken, everything in that path stops working. You might remember light bulbs of many, many years ago on Christmas trees, where if one bulb goes out, the whole string goes out. Well, today's light bulbs are wired a little differently. They're wired in a parallel circuit, so that doesn't happen. But a long time ago, that did happen. So here's an example of the series circuit. You have your battery, you have all your load on that single wire. In this case, we have light bulbs. And if that one light bulb goes out, doesn't matter which one it is, they're all going out. All right. Now in a parallel circuit, that's not going to happen. There are several branching paths for that electricity to flow. Here's our example. Notice how it's different. Each of these bulbs is on their own circuit. So if we disconnect or one of those light bulbs goes out, the other three are going to work. Today we're going to be using a battery in our lab to assist us in our electrolysis and our electroplating process. So batteries are composed of a chemical substance that can generate voltage, which can be used in a circuit. And modern batteries, lithium-ion batteries, alkaline batteries, all store energy. And they have a zinc container of the dry cell that contains a moist chemical paste surrounding a carbon rod suspended in the middle. And electrons easily flow in and out of that small chemical reaction. All right, so electrolysis is going to be using that battery and hooking up one wire to each end, so 2 wires total. And what's going to happen is we're going to watch the flow of electrons move through that circuit. However, it's going to be moving through a solution, through a liquid type solution. And in fact, we could use that to our advantage to do some work and some pretty cool things. So electrons are flowing from the negative side to the positive side, and in doing so, we're going to be taking out copper ions from our solution and putting them on another piece of metal that didn't originally have those copper ions. All right, sound exciting? All right, let's go try it. All right, boys and girls, welcome back to the shop. Today we're going to be using electricity in other ways than what you're normally used to. Like this. Or this. Or even this. Or this. Or this. Ooh, I think I'll have one. So, have you ever seen the bumper of a classic car like this one? Or a big red fire truck, and it's all shiny and almost mirror-like? Well, today, I'm going to teach you how that process works, and you could do it at home. let's go ahead and get started. So today's experiment is going to be done with common household items. Now we're going to be using electricity in a non-conventional sense. We're used to using electricity to, as you saw, turn on our light bulbs, power our equipment, and run our appliances. Today we're going to be using electricity to copper plate some coins. Okay, so in order to get our metals to stick together, we need to go through a process called electrolysis and electroplating. Today we're going to be electroplating with copper, and we're going to get copper to stick to this quarter. I have a materials list right here, and some materials you're going to need are vinegar, a clear cup and a clear jar, preferably one plastic and one glass, rubbing alcohol, a 9-volt battery, 2 copper strips, and I've also included some copper mesh, 2 alligator clips, 2 wires, some electrical tape, hydrogen peroxide, and a measuring cup. Now, my glass jar is itself doubles as a measuring cup, so we're just going to go ahead and use this. Remember, whenever doing a science experiment, it's 100% necessary to be safe and have adult supervision, just like you would in the classroom if I were there with you setting this up. Alright, for you folks trying this at home, we're going to go ahead and prepare our battery. Alright, what we're going to need is our 2 pieces of wire, our battery, and some electric tape. And I'm going to stick our red wire to the positive terminal on our battery. So I'm going to take this here, I'm going to put it on here, and I'm going to take our electrical tape, and I'm going to attach it to that terminal, just like so. And I'm going to bring the tape down. I'm going to make sure that these 2 leads do not touch. I'm going to take my yellow wire and I'm going to attach it to my negative terminal. Okay. Make sure you do not allow these 2 wires to touch. Alright, next I'm going to prepare our solution. And what I'm going to do for our purposes here in my shop is I'm going to use vinegar, and I'm going to add just a little bit, roughly 1 inch to the bottom. I'm going to add an equal amount of hydrogen peroxide. Now, with our solution set up, we're going to take our battery and our alligator clips. We're going to take the yellow wire and attach it to our negative end, which represents by the black alligator clip. And we're going to take our red wire, which represents our positive terminal, and connect it to our red side of the alligator clip. Now, in order to make the electrolyte, we're going to take both our copper strips and we're going to attach them to both the positive and the negative terminal. Now, we're going to drop these in the solution, making sure they don't touch. Okay, this part of the experiment takes the longest. You're going to want to let this sit for about 3 hours before you go ahead and start the electroplating process. Now, once the 3 hours is up, what you're going to do is and this has to be in this order, you're going to take the black, what's called a cathode, you're going to take the black cathode out, okay, make sure you don't touch it, so just open up that alligator clip, let it fall, then you're going to attach the quarter to the clip, put it inside of the solution, and wait another half hour. What's going to happen is those positively charged ions inside of your solution are going to be attracted to your quarter, and then you're going to pull your quarter out. Now, we don't have time to wait. So what I'm going to do is I'm going to supercharge this experiment with some fancy equipment that I have here in the shop. Okay, Now, I have our solution, and I did something a little special to it. Now, what I'm going to show you what happens when I add our copper mesh, it's going to be a chemical reaction. Now, I can't disclose to you what exactly I did to it or how I'm going to do it, but if you follow my procedure and my steps for how I want you to do the experiment at home, it should work just fine. This is just going to speed it up a little bit. So what I'm going to do is I'm going to actually bring you down here. I'm going to add this to our jar, and I'm going to show you what happens when we go ahead and speed this process up. So here we go. All right. If you check it out, we have a chemical reaction going right now. Our copper is being dissolved into the solution, and it's actually turning blue. That's a good thing. Okay, remember, those positive charged ions in the copper are dissolving into that fluid so we can attach them to our quarter. Now, what I'm making here is a solution called copper acetate. All right, I have my electrolyte solution, my copper acetate, and what I'm going to do next is prepare our positive and our negative lead, and hopefully, if all goes right, electroplate this quarter so it's the same color as a penny. Now we want to make sure our quarter is free of any oils or contaminants. So this is where the isopropyl alcohol comes in, and we're going to get that quarter nice and clean. Notice that my alligator clips got a little larger. All right. I don't want to touch it because the oils on my skin might contaminate it. I'm going to go ahead and turn my power supply on. What I'm going to do is I'm going to pick up this quarter with my negative lead. I'm going to put it in the solution. All right. It's been roughly 15 minutes now. Let's see. Check that out. Copper plated quarter. Electrolysis at work. Now I want you to give it a shot. What did we learn today? Well, we learned that electricity can do more than provide us the ability to power lights and appliances and use our cell phones. We created an acidic aqueous solution of positively charged copper ions called copper acetate using vinegar, hydrogen peroxide, and copper. And then we used those positively charged ions in solution, which were attracted to the negative charge on our coin, thus allowing us to electroplate it. As always, stay safe, and thanks for watching. We'll see you next week.